The James Webb Space Telescope is catching surprisingly bright galaxies just 320 million years after the Big Bang, way ahead of schedule according to every model we have. Hubble data once suggested a star that nearly tied the universe's age in a cosmic photo finish, and quantum experiments reveal correlations so strange they feel like time travel, even though they're not. These aren't measurement errors or internet myths. They're peer-reviewed observations that push the boundaries of physics so hard that scientists are rewriting textbooks in real time. And here's what makes these paradoxes so unsettling. The more precisely we measure them, the stranger they become. Each new observation reveals not answers, but deeper questions about whether our universe actually makes logical sense. The impossible early galaxy paradox. We expected the early universe to brighten slowly as the first stars formed over hundreds of millions of years. Instead, JWST keeps spotting surprisingly mature galaxies just a few hundred million years after the Big Bang. Not older than the universe, but way ahead of schedule. Galaxy candidate JADE's GSZ 13-0 exists when the universe was only 325 million years old. At this redshift of Z approximately 13, we're seeing a compact, unresolved object that somehow assembled massive amounts of stars in record time. Early dramatic claims about Z16 galaxies were later revised to Z 4.9 with better spectroscopy, but even the confirmed high redshift objects shouldn't exist this early. The gravitational physics required to pull together enough matter to form these bright galaxies simply didn't have enough time to operate. Dark matter halos needed to collapse, gas needed to cool and condense, and massive stars needed to form and begin nuclear fusion. According to our best models, this process should take 800 million to 1 billion years. But JWST sees compact, rapidly forming galaxies at Z greater than 10 that challenge every timeline we've calculated. These observations suggest either our models of early star formation are fundamentally wrong, or something accelerated cosmic evolution in ways we don't understand. The implications extend beyond astronomy. If galaxies can form this quickly, it suggests the early universe was far more efficient at creating complex structures than our physics predicts. We might be missing entire chapters of cosmic evolution. The Methuselah near-miss paradox. For decades, astronomers tracked a star that seemed to challenge cosmic chronology itself. HD 140283, nicknamed the Methuselah star, initially appeared to have an age that overlapped uncomfortably with the universe's own 13.8 billion year timeline. Hubble data once suggested a near tie with the universe's age, creating a cosmic photo finish that made headlines worldwide. How could a star be nearly as old as existence itself? But here's where careful science trumps sensational claims. Updated models using Gaia satellite distance measurements and improved stellar evolution calculations place HD 140283's age safely younger than 13.8 billion years, around 12 to 13 billion years old. The paradox dissolved under scrutiny, but it revealed something profound about the precision required in cosmic measurements. When you're measuring objects billions of years old, even small uncertainties can create apparent contradictions that take decades to resolve. HD 140283 represents one of the universe's earliest stellar generations, formed when the cosmos contained almost no heavy elements. Its near-record age offers a window into cosmic dawn, even if it doesn't actually predate the Big Bang. The information hiding paradox. At the edge of every black hole, one of physics' greatest mysteries plays out in real time. For 50 years, scientists debated whether black holes permanently destroy information about everything that falls into them, violating quantum mechanics' most fundamental principle. Here's the classic setup. When matter crosses a black hole's event horizon, it carries information, the exact quantum state of every particle. According to Einstein's general relativity, this information becomes trapped forever behind the event horizon. But Stephen Hawking proved that black holes emit radiation through quantum fluctuations. Virtual particle pairs appear at the event horizon, one particle escapes while its partner falls in, and over vast timescales, this Hawking radiation causes black holes to evaporate completely. For decades, it looked like black holes erase information completely, since Hawking radiation appeared completely random. But modern calculations reproduce the page curve, a mathematical prediction showing that information actually leaks out in subtle quantum correlations within the radiation. What looked like information destruction now seems to be information hiding. Recent calculations by physicists like Leonard Susskind suggest black holes drip out secrets in quantum patterns, not classical signals. The information escapes, but encoded in correlations so complex we're only beginning to understand them. The paradox isn't fully resolved, but the mathematical evidence strongly supports information conservation. Black holes don't murder information. They encrypt it in ways that require quantum computers to decode. The quantum correlation paradox. In 1701, Thomas Young performed an experiment that revealed light's wave nature by firing it through two parallel slits. Modern quantum versions of this experiment create patterns so strange they feel like evidence of time travel, even though they're not. When physicists fire single photons through two slits, they create interference patterns that suggest each photon somehow passes through both slits simultaneously. But the moment anyone tries to determine which slit the photon uses, the interference pattern vanishes. Delayed choice experiments take this strangeness to extremes. Physicists can decide whether to observe a photon's path after it has already hit the detector screen. This future decision seems to retroactively determine whether the photon exhibited wave or particle behavior in the past. No, your mind isn't rewriting history. Delayed choice experiments reveal how measurements are correlated, not messages traveling backward in time. The retrocausality emerges only when physicists post-select data from entangled particle pairs. But the correlations are real and profound. Quantum mechanics allows particles to exhibit properties that seem to depend on future measurements, even though no information actually travels backwards. The universe maintains consistency through correlations that transcend our everyday understanding of cause and effect. The universe appears calibrated for complexity with suspicious precision. Small changes to fundamental constants can drastically change stars and chemistry, but precise percentage thresholds depend heavily on which model you use and whether you adjust one parameter or several simultaneously. If the strong nuclear force were significantly stronger, stars would burn through their fuel before planets could form stable orbits. If it were much weaker, stars couldn't create elements heavier than hydrogen. The electromagnetic force, gravitational constant, and electron mass all exist within ranges that allow complex matter to exist. Physicists debate how tight these constraints really are. Some changes break stars and chemistry catastrophically, while others can be offset by adjusting multiple parameters simultaneously. The real story is nuanced and depends on sophisticated calculations that consider parameter interactions. Some propose the multiverse hypothesis. If infinite universes exist with every possible combination of physical constants, we naturally find ourselves in one where consciousness can evolve. But this creates the Boltzmann brain problem. Most conscious observers in such a multiverse would be random quantum fluctuations, not evolved beings in stable universes. The fine-tuning debate continues because both the multiverse solution and design implications challenge our understanding of probability, consciousness, and cosmic purpose. The universe has revealed its most profound deception through precision measurements. Observations indicate roughly 68% dark energy, 27% dark matter, and only 5% ordinary matter. Everything we can see represents a tiny fraction of reality. Dark matter outweighs visible matter by more than 5-to-1, forming the gravitational scaffolding that allowed galaxies to form. Yet despite decades of increasingly sophisticated experiments, we cannot detect it directly through any force except gravity. Dark energy is even more mysterious. If dark energy behaves as a cosmological constant, its density remains constant as space expands. This means the total dark energy content increases with cosmic volume. Not because energy is created from nothing, but because that's how general relativity works with W equals -1 equation of state. Here's the paradox. Both dark matter and dark energy have precisely the values necessary to create a universe where galaxies can form and conscious life can evolve. Too much dark matter would cause gravitational collapse before stars could ignite. Too little would prevent galaxy formation entirely. We have no theoretical basis for why these invisible components should possess exactly the right properties to enable our existence. The cosmic inventory appears fine-tuned, but we don't know whether this reflects deeper physics, observer selection effects, or something else entirely. The meta-paradox resolution. These paradoxes share a common thread. They emerge at the boundaries of our observational capabilities and theoretical understanding. Each represents a place where reality pushes against the limits of current physics. But notice what happens when we apply rigorous science. The Methuselah star paradox dissolved under better measurements. The information paradox appears to be resolving through advanced quantum calculations. Early galaxy observations are forcing us to refine, not abandon, our models of cosmic evolution. The universe doesn't just contain paradoxes, it contains the tools to eventually understand them. Every apparent contradiction becomes a research program. Every impossibility becomes a question worth investigating. What we call paradoxes might simply be previews of future physics. The quantum correlations that seem impossible today could become the foundation technologies of tomorrow. The dark components that perplex us now might reveal new fundamental forces. Science advances by transforming paradoxes into understanding, and perhaps that's the most profound realization. The universe isn't broken by contradictions, it's driven forward by them. Reality is paradox in the process of becoming knowledge. Each impossibility we observe today could be the key to unlocking tomorrow's breakthrough, and that might be the ultimate truth about our universe. It stays ahead of our understanding just long enough to keep us searching for answers. The cosmos doesn't present paradoxes to frustrate us. It presents them to guide us toward deeper truths we haven't discovered yet.